Hello and welcome back to the lectures on applied econometrics. We have been talking about decision making when it comes to hypothesis testing, and we talked about several tools that we use when it comes to decision making during the hypothesis testing. And those tools or basically concepts that we use are level of significance, confidence level, p-value, power, the properties of the distribution, and something called confidence interval. And we'll see how we actually derive confidence interval from the other tools like confidence level. Okay, let's begin with that. Now when I say confidence interval, there is something we have to understand, and basically we have to understand what it is not. All right, so let me explain that. So when I say so basically confidence interval and confidence level are pretty close concepts, and I'll just explain that in a while. Let's say I say that a 90% confidence level, okay, a 90% confidence level, what it means is that let's say the statement goes like that: a 95% confidence level for a population mean to be within 100 and 200. Okay, so that is the confidence level attached to this statement, that my population mean is within 100 and 200, and I have a confidence level of 90%. Okay, now what it does not mean is that it does not mean 90% chance that the population mean falls between 100 and 200. It does not mean that 90% chance, the chance factor, it does not mean there is any chance factor of 90% for the population mean to be within 100 and 200. And the reason is population mean is also always fixed, right? Population mean is always fixed. It's fixed, right? Is fixed. So either there are only two possibilities. Population, because it is fixed, there are two possibilities. Either it can be in the range of 100 to 200, so either it is here, or it is not here, or it is somewhere outside. So if it is in here, so I will have a probability of population mean to be, let's say x, to be within 100 and 200 is equal to 1 here, or is equal to 0. Okay, so only two possibilities. It is either 1 or 0, because there cannot be a chance factor attached to something which is fixed, right? It is already fixed. So that is something we have to remember. So then if it is not involving any chance factor, so what it is really involving? So it is basically how we really understand it is that we say that 90%, so we said 90%, right? Not 90%. So we say that 90% of the time, 90% of the time, we create the interval using sample statistic. Here is a mean, it could be proportion, anything, using sample statistic. The interval will contain the population mean. The interval will contain the population mean. Okay, contain the population mean. So basically you have to understand what is varying here is the sample statistic. So every time you get a sample statistic, you have certain technique to construct the interval. And when you construct the interval, when I say 95% confidence level, that means 90% of the time you construct the interval, you will have the population mean within that interval. So let's say I take sample mean 20 times, sample mean 20 times. So what it would mean if my confidence level is 90%, 18 out of this 20 times, 18 times the confidence interval will contain the population mean, or population statistic, whatever that is, population mean here. Okay, and I'll illustrate that with a diagram in a while. Now, so I hope you understand it. So essentially, if we say that it is 95% confidence level, so then there will be 19 times out of the 20 times you create that interval that will contain the population parameter. Okay, okay, great. So now let's try to actually illustrate that with an example. And let's say we are, sort of getting the height of the students. So let's take an example. Let's say height of the students, and we want to basically get the confidence interval height of the students, and we basically pick samples, and out of using this sample we will create the confidence interval. Okay, and whatever we have just discussed, we'll just demonstrate that. Let's say I have a population parameter. Let's say I know about this population parameter, and I usually denote the population parameter with a mu. Let's say it's a mean. So mu is, let's say, 172 centimeter. So that's the height of the students. Let's say in a school or whatever, classroom, or in a village, in a town, whatever that is. Let's say in a town. Okay. Let's say this is age maybe 12 to 14 in a given town. I'm getting the mean height of the boys or girls. So I get that that's, let's say that's 172 centimeter. Usually we don't know the population parameter, but let's say we know it. Okay, here. Now what I do is I can't really go to every household and actually measure everybody's height. So what I do is I basically take three samples, three individuals I take, like n equal to 3, my sample size, and I take three individuals and I get the mean. Okay. So let's say the first three candidates I get, I will actually write down this. So let's say first draw, that is different color. First draw. What are the different observations I have? Let's say I have 172, 173, and 165. And if I take average, I think I will get the mean is equal to 170. Okay. So that's basically my X bar. So that's the different observations I'm getting. So let's say first draw, so X bar 1, and that's equal to 170. Okay. Now I have a second draw, and I see that three observations I get 177. Let's say 172, and then I have 171. And I think if I take a mean, it is going to give me a value of 173.3, right? So basically 170, and then 7 plus 3, 2 plus 1, 10, and 10 by 3 is 3.3. So that's my X2 bar. I get this. Reduce the size of the window. Let me use it further, or maybe I can just keep a value. So third draw, I'll go for a third draw. And in this third draw, let's say I have 3 over 168, then I have 171, then I have 175, let's say. And if I take a mean of all this, I will get, I guess, this is going to be 170, 171.3, I think. 171.3, okay. And this way, let's say I draw it 20 times, okay. And let's say that in the 20th draw, my observation is 170, 172, and 171. All right, and the average is going to be 170. Let's say 170. This is going to 171, right? 171. So X bar, X20 bar is going to be 171. So I got all the different sample means, right? And I will construct the confidence interval using the sample means. And let's do that. Let's do that. So let me now actually draw a distribution where I already have, this is the original distribution of all the samples, and let's say this is a true population parameter. Mu is equal to 172. Okay. Now, when I create the confidence interval, how I really do that? How I do that is, let's say every time when I draw this different samples, so let's go back to the numbers here. So the first draw I got 170. Okay, I got in the first draw I got 170. In the second draw I got 173.3. In the third draw I got 171.3. In the fourth draw I got 171. Sorry, it's the 20th draw. But other draws also we got several values. So when I say it's a 90% confidence interval, so what happens here is 90% confidence level. So what happens is, so in the first draw I got 170, right? So I create a confidence interval. So there is a formula, right? There is a formula using X bar. You can actually have an interval, and we're just going to see the formula in a while. So what I create an interval. Let's say this is the interval I got. So essentially, I will find that this mu to belong in this confidence interval. Second time also you get some X bar, and you create some interval. Let's say it's like this. But the interval might like change its location in the sense that whatever is your X bar, but end of the day that interval is actually containing the value mu. 172 is within this interval. Similarly, third draw, fourth draw, and when it's a 90%, so I can say actually what is happening here is that out of this 20 draws, 18 times I'm actually getting the mu within this interval. So there might be one case where my interval is falling here. There might be another case where my interval is falling here. It doesn't mean like it has to be on the right or left. It could be on the same side or whatever. But end of what we actually mean is that out of the 20 times, 18 times my interval is containing the mu. Okay. So that's basically the idea of confidence interval, and that's how it is related to the concept of confidence level. Okay. All right. Okay. So here we see now we'll see how we really create this confidence interval. And essentially, you have to remember that we use the mean. Let me use a different page here. Sample mean. What you need is a sample mean. Sample SD. We do not know the population standard deviation, so we use the sample SD to basically approximate for the population SD. Okay, and using this we basically create and we of course need to have a confidence level. We need to have the confidence level, so which will give us the kind of margin of error we want. So let me just explain that. So sample mean is essentially it could be any other statistic. So basically the statistic, we need one statistic. Okay, then we need the confidence level. This will be given, and the sample SD will help us to understand the margin of the error. Okay, margin of error. So essentially margin of error would be derived by this too. Okay, so we need the sample statistic, and then we need a margin of error which will be derived from sample SD and the confidence level, basically from sample SD to population SD, and this will help us to get the margin of error. Okay, population SD and the confidence level together will give us the margin of error. All right. So the formula here is that confidence interval is equal to whatever statistic we have plus minus the margin of error. Okay, margin of error. So usually we calculate the margin of error with the help of basically our confidence level and the standard deviation of the population. And since we don't know the standard deviation of the population, we approximate it from the sample. So the formula that we get is, let's say, confidence interval for the population parameter, population mean. We will have, let's say, T alpha for alpha level of significance, and this is the sigma by root n. Okay, so we basically use the sample statistic S, and we sort of use that as sigma and a correction factor of root n. Okay. Um, Okay, all right. Now, one thing we have to see, oftentimes we use a t statistic instead of a z statistic, even though we actually assume the population to be normal, the distribution to be normal. The reason behind this is when we deal with the unknown population parameter, we use a t statistic instead of a z statistic. Z statistic is something that we use when we have known population parameter. Okay. Okay. Now, what we can infer from this formula is that if I have a high standard deviation, my confidence interval is going to be wide, right? If I have a high standard deviation, my confidence interval is going to be wide. Whereas if I have a high n sample size, my confidence interval is going to be narrow, right? Now, we will prefer a confidence interval to be narrow because the confidence interval is narrow means within that I'll be more sort of, I'll be able to say that within that narrow range my population parameter belongs. So I'm kind of more certain where my population parameter is. But if it is very wide, then it could be anywhere, right? It could be anywhere. So that is something that's not very helpful. But if I have a narrow confidence interval, then it's actually helpful. And that is the reason why we need, we usually prefer uh, a small sigma. We usually prefer a small sigma and a large n, right? The sample size large is usually good, and of standard deviation, low standard deviation is usually good, right? Okay, so how we construct the sample, the confidence interval? So by now we understand that we have to choose a sample statistic, be it a mean or be it a proportion, and then we have to choose the confidence level. So depending on the confidence level, I get the t statistic, and I know how the confidence level and how to see the confidence basically t statistic corresponding to a confidence level, and we're going to see that in a while when we do an example. And then we basically get the margin of error, and finally we actually obtain the confidence interval. Okay, now let's do one example to basically see how we really construct that. Okay, uh, so let's say the problem we have in hand is, let's say we have a sample. Let's say we are like, you might be knowing the Hilsa fish in, Padma River, or the in Ganga River also. I think mostly in Padma River. Let's say it's Padma River. Padma is famous for Hilsa fish, and we are interested to know the mean weight of the Hilsa in this year. Okay, during monsoon season, people just go for sort of fishing, and Hilsa is really a high commercial value, and a lot of people actually end up fishing like small Hilsa fish and so forth. So we are interested to know the mean weight of Hilsa fish in Padma River this year. Okay, let's say we have fish weight. Let's say we have collected some samples, and we get a mean fish weight is 900 gram. Okay, and the standard deviation for the fish, all the different fishes we got is 300 gram. All right. Now and let's say we have actually, say, we got around 1,000 Hilsa, and we got this these different values for mean and standard deviation. And let's say we have a confidence level given to us is, let's say, 95%. Okay, now we have to create a confidence interval for the for basically obtaining the weight of the basically Hilsa population in Padma River. Okay, so if I write down in all these different information in terms of notation, so I'll write x bar is equal to 900, s is 300, alpha is equal to, this is the level of significance, which is 1 minus confidence level is 5%. And for, because we know that we are going to use a t-statistic, we really don't know the population parameter, so I have to also have the degrees of freedom. And if you remember t-statistic, the degrees of freedom is going to be n minus 1, which is 999, right? Okay, great. So, and of course we are given the confidence level, CL is 95%. Now let me actually try to see the, I have too many windows open here, but um, let's see, we want to get the t-table. Let's get a t-table, okay? T-table, let's say t-table PDF. Let me get a PDF here. T-table, I got a t-table here. So we know how to see a t-table. We have to see the degrees of freedom. Along with that, we have to see the value of or the t-statistic. And here, since I have just one thing you have to remember, so this is basically, if we consider a two-tailed test, the 95% what is given here. So essentially, if I draw a distribution, it will look like this. It's not really great normal curve, but yeah. Let me try it again. Okay, or something near normal, let's say. So if I draw it, I will have, so 95% is this region, right? This region under this curve. And since it is symmetrical one, the 5% will be spread across both these sides, and this is going to be, let me actually make it more prominent. So I fill this, and this part is going to be 2.5%. This part here is going to be 2.5%. Now when I see the t-statistic, I'll see the t-table, so I'll see that they have given a cumulative probability. So cumulative probability for 95% confidence interval, I will basically consider only up to this, and that will be from here, right? So that is going to mean that means cumulative probability is going to be for 97.5%, right? Because I'm talking about the cumulative probability now. So it is only here up to here. The probability value will be taken up to here, right? Which is 97.5%. Now let's look at the t-table, and we need to look at the t-table for cumulative probability for t-statistic is equal to t.975, and we know how to see a t-table. So let me just actually go to that. So in case of t-table, we need to basically look into the cumulative probability or cumulative probability and the degrees of freedom, okay? And the degrees of freedom in this case is going to be, as we have seen, is 999. Now we can look at the DF, which is on this row, and all these DF values we see it is from 1 to, and then it has gone up to 100, and then suddenly it has jumped to 1000. Now since our DF is 999, it is close to 1000, so we can basically approximately take the value corresponding to the DF of 1000, and the value is going to be, now the value is going to be 1 point, so this one, let me just again, so t.975. So if I just go down here for 1000, it is going to be 1.962. You can approximately say, let's say 1.96, okay? And let's just go back to our calculation table. Let's go back to our calculation table, and here, and we see that for t-stat, t is 0.196. We have then we get those, sigma by root 10 value, which is 300 by 100 square root of 100, which is 30 by root 10, and which is essentially around 9.49 or 9.5. Okay. Now you take this and then you do the rest of the calculation. So you basically use a formula. You have your x bar, which is 900 gram for the average weight, and then you substitute the value, and then you have the t statistic is 1.96, and then sigma by root n is 9.5. Now if you just do a plus and minus here, so you basically get the interval, and that is going to be 1.4 to 8.6. So that is how you basically get the confidence interval. So with this, we'll end this lecture here, and in the next lecture, we are going to see a couple of more examples of confidence interval.